Welcome back to TRB Polytechnic EEE Solutions. We'll go ahead with the problems. So we are addressing one more problem from the electrical paper. Yes, the next one more problem from control system. So first understand what is given: a cascade forward path compensator designed for a system having a transfer function. That means what is given is transfer function of the compensator. Okay. So what is the compensator given? First understand what is a compensator given. So this is your 0 and this is your pole. So 0 is at minus 0.05. Pole is at minus 0.005. Okay, that means pole is here, 0 is here. So it's minus is at, that's your minus is at minus 0.05. So it is minus 0.005. Okay, that means, so let me say this is S plus Z. S by Z means S. So what is the structure then? Pole is greater than 0, or let me write this in the form of S plus Z by S plus P. So is greater, Z is greater than P. So Z is greater than P means it's a lag compensator. It's a phase lag compensator. Okay, so yes. What will happen if we use this lag compensator? Okay. So first understand the structure. So we have a closed loop control system. So here we have GC of S. Here we have the transfer function of the plant or the system to be controlled. Let me take it as GP of S. So that the net forward path, I will take it as G of S. That's intention. So assume it's a familiar unity feedback structure. He didn't talk about it, but still, okay, it's just have a view of a closed loop control system. So this compensator will improve what? Okay. So it's 0 greater than pole means it is going to offer a lagging. That means usually lead actually improves stability. Lead actually, there is phase lead compensator improves stability. That means it is going to improve damping. Damping is getting increased. The moment we add lag, damping is getting decreased actually. Okay, stability is getting decreased. The moment you feel stability as well as the available margins, in fact, the phase margin, okay, phase lag means it's adding a phase lag means effectively we are going to decrease the phase margin. So phase margin decreases means damping is going to decrease. So lagging, it is destabilizing act. So the stability decreases means you can feel like a friction in the system is decreasing. Damping decreases. As a damping decreases, so improve means it is not going to improve damping. So B is wrong option. So we'll go for wrong and right statements given. So its damping is not getting improved. Then steady state error, it won't touch because steady state error depends on the type of your G of S, H of S, or the number of integrators available in the loop. Okay, then peak overshoot of the system. Yes, the point is this: as the damping decreases, automatically the percentage MPO will increase. It's not improving actually. Okay, right? It's not improving. So it is improve the following means it is. So there is two options. Either you have to go with the option A and we have to go with the none of the above options. Okay, right? So improve what? Improve means, so increase in peak overshoot is not an improvement. Increase in peak overshoot is not an improvement. Overshoot increases is not an improvement. So will increase is correct, but here improve is the meaning. So because you can remember the expression percentage MPO is equal to e power minus zeta pi by root of 1 minus zeta square into 100% is your overshoot. So the overshoot will have something like this. This is, for example, zeta, and this is your percentage MPO. If you plot this, then zeta 0, zeta 1. Okay, between undamped and critically damped condition, the overshoot will fall from 100% exponentially. It will fall from 100% to 0%. Okay, like that. So what's happening is damping is decreasing means overshoot is increasing. This is not an improvement. Okay, so the compensator will improve what means then I will go with option D. Okay, I'll go with option D. It is going to increase the overshoot. It is not an improvement. So improvement means the overshoot should decrease. That's an improvement. So peak overshoot of the system is getting increased. So it's not an improvement. So none of the above options is a correct answer. Okay, I didn't check the other keys. Okay, so I'll go with option D for this problem. Okay, so the lag compensator is getting introduced. Okay, the zero is greater than pole. Okay, therefore it is going to destabilize the system. I'll feel like the damping is getting decreased as the damping decreases because we don't know the order of the system and all. So we have to conclude means this is the possible way. Damping decreases means assuming it is a second order or higher order, I'll go with the option D because the overshoot is getting increased. So that means transient performance is getting degraded. Okay, so we are going to get a degraded transient performance. Okay, because as the overshoot increases, the transient performance is not getting improved. Okay, right? He used a word improved. So I'm not going with option A. So I'm going with option D. So option D is the best possible answer for this problem. Okay. It won't influence steady state error because only integrator will do, because it is not offering any integrator. So it won't influence the steady state error. Maybe you can think of playing with the KP. Okay, right? If you play with the KP for that also, we should know what is your GP of S and all. So just have a think about whether it is improving steady state error or not. So for that, steady state error means with respect to what input? There are multiple inputs. Okay, so then you can assume a common input, step input, assuming step. Okay, then ESS step means ESS will be equal to what? 1 by 1 plus KP you will get, assuming unit step, and KP you know that is limit S tends to 0, S into no S for this, it is going to be G of S, H of S. So G of S, H of S. Okay, so H of S is 1, so let it be. So then, and I have what is the resultant mean? G of S alone is there. So limit, I'm just checking, is it okay? GC of S and GP of S. So assuming no integrator in GP of S, it will be GP of 0, and GC of 0 will be if the compensator is not there. If say compensator is there, I'm letting S equal to 0. That means it's 0.05 by 0.005 into GP of 0. Okay, it is going to have some value, but this value getting decreased by what? 0.05 by 0.005 will be, so it's going to be 1 by 10. So it's 1 by 10th of your GP of 0. What is happening because of this? So the KP is getting decreased. As the KP getting decreased, error will increase. Error actually will increase as the KP is not getting improved. It is getting decreased. So error will increase because KP value decreases. So it's also, so I thought in different direction, it may improve the steady state error. No, it is not going to improve the steady state error also. It is also going to increase the steady state error, steady state deviation between the input command and output response. Since it is unity feedback, that statement is fine. Okay, so the best possible answer for this problem is option D, none of the options. So the compensator is not improving anything. Okay, so damping factor, it is touching. Okay, right? It is decreasing the damping factor, not increasing. So it's not improving. Improving means, so improving the damping factor of the system means what? Damping increases mean there is an improvement. It's all related to the transient response only. Okay, so damping factor as well as peak overshoot both are okay dependent parameters. Okay, right? If there is an improvement in damping, friction increases, then automatically the peak overshoot also going to get decreased. That's an improvement. So if it is a lead compensator, you can give the answer both A and B. If it is a lead compensator, both are correct. A is, there is improvement in damping, there is improvement in peak overshoot. Both will become correct since it is a lag compensator. You can't choose A and B. So the choice is D. Justified. That's a correct answer. Okay, so let us hope the key is also the same. Okay, right? Next problem is the resistance is classified as a low resistance. Okay, so it is classified as low resistance. Okay, if it is of value. Okay, so low resistance means less than 1 ohm. Medium means up to kilo ohms, and high resistance means in the order of greater than kilo ohms. Maybe you can perceive like 1 kilo ohm. So greater than 1 kilo ohm, we can call it as high resistance. Okay, so medium resistances usually we measure by using bridges apart from ohm meters. So bridges, okay, so Wheatstone bridges for medium resistance measurement, and low resistance always we use Kelvin bridge. Low resistance, okay, Kelvin bridge, Kelvin single arm bridge, okay. And if you want to make an improved accuracy, then you have to use Kelvin double bridge. Kelvin's double arm bridge is a way to measure low resistances. Probably that's where you talk about low, medium, and high resistances. Okay, high resistance will be measured by using an instrument known as megohm instrument. So Kelvin's double arm bridge, okay, double bridge shortly we call as the instrument for low resistance measurement. So the right answer below 1 ohm, okay, is the correct answer for this problem. Okay, that's very simple and straightforward. Okay, then the shunts are made of. Shunts are made of. Okay, so usually shunt means where we use mean shunt is always the one which is connected in parallel. Okay, shunt is nothing but the one which is connected in parallel. Here a shunt means it's basically belong to a meter extension. A meter extension. You are extending the range of an ammeter. Say for example, I have an ammeter of 0 to 10 milliamps. So then I have a meter resistance of say for example 100 ohms. But I want to measure a current of, for example, at 20 milliamps. Okay, full scale. I want to measure 0 to 20 milliamps, but actually the instrument cannot. But I'm going for that. Okay, so that means when it is 20 milliamps, the meter should get 10 milliamps. So meter should be at full scale deflection. Then whatever the reading, I will multiply by 2. So I'll call this as a multiply by 2 point. That means the meter can take only 10. So rest I need to bypass by using shunt resistor. That's what we call as a shunt. Okay, the shunt resistor is designed such that it is going to handle the same current. Okay, and since meter resistance and meter and shunt are in parallel, okay, and that too they have identical currents in this case, then R shunt will be equal to what? Rm. Okay, then usually the R shunt will become less than Rm if the current in the shunt, I shunt, is greater than the meter current, the full scale deflection current. Usually it is. Say instead of 20, to show that, I'll go for the 50 milliamps instead of this. So it's 50. This is 50 means how much I need to bypass? I need to bypass 40. So 40 milliamps I need to bypass, but both are having same potentials. Then tell me what will be the R shunt in this case. So that's a real situation. You'll understand the role of R shunt. So what is the voltage across this? So it's 10 milliamps at full scale across 100 ohm will make what? 1 volt. Okay, so therefore the voltage across this also is equal to 1 volt. 1 volt across R shunt. That's how we can go for the shunt resistance. So it's 1 volt. By sensing 1 volt, it has to bypass 40 milliamps current. Okay, when the full scale current of input is happening 50 milliamps. So then it is going to be 1000 divided by 40 ohms. You will get 1000 by 40 will be 25 ohms. Okay, probably one may remember R shunt is equal to the meter resistance divided by the multiplication factor minus 1. So here the multiply by is, so it's into, it is 10, you're going up to 50 means it's into pi, that into 5 it's a multiply by factor. So that M is the multiplication factor, M refers your what is your IFSD, what is your I you are about to measure divided by the full scale deflection current of your instrument. I you are measuring is 50 and the full scale deflection current is 10. So it's going to become 5. So then Rm by 100 by 5 minus 1 also you can go for the calculation, but I went with the fundamental. Okay, do not remember any expression. With this you can connect. Yes, the problem is talking about that shunt only. The problem is any metal wire subjected to change in temperature is going to have the expression RT equal to R naught into 1 plus alpha T. So any metal going to have a positive temperature coefficient alpha, what will happen is as the resistors temperature, because this is always having a current passing through it, always there is a power dissipation, and external temperature also will influence. By mistake, if the shunt resistance increases, If the shunt resistance increases, if R shunt increases, what will happen? I shunt will decrease. I shunt will decrease. When I shunt decreases, IM, the meter current will become more than IFSD and inviting complete damage for the pointer. Okay, the pointer will hit the full stop. There will be a full stop in the scale practically. So the pointer will hit the full stop and the pointer will become bent. Okay, if no full stop is there, but still it is going to generate a huge torque beyond the torque needed for the full scale displacement. Therefore, so to ensure the safety of the instrument, the current through the instrument should be never beyond the full scale deflection current. At any cost, we need to protect our instrument first. Okay, once the instrument get damaged, then we can't make any measurement. Therefore, you should never allow a current through the instrument more than what it is capable of, full scale deflection current. Okay, so therefore the shunt material should be made up of, okay, shunt material should have alpha such that it is closer to 0. That means what? Any temperature variation will not affect your shunt resistance. That means will not affect your I shunt, okay, as per the design. Therefore, shunts are made up of materials which are temperature insensitive. That's a fundamental behind this problem. Okay, once you know that, it is straightforward. And who is temperature insensitive material means, who is temperature insensitive material? Manganese is temperature insensitive material. Manganese or constant 10 are the two materials. Okay, constant 10. Okay, check the spelling. Constant 10 are the two materials. Okay, so almost temperature insensitive material. Okay, so by default, okay, we use temperature insensitive material for shunt, sometimes for R series also, in multipliers also. Okay, right? Okay, that's a point. Okay, here temperature is coming into the play, so there should not be any temperature effect. Okay, while for your R shunt especially. Okay, but the meter resistance definitely will vary with respect to temperature, because it is going to be made up of the material which we use in PMMC, maybe a copper coil. Okay, so it depends on your moving assembly. Okay, right? So we'll talk about one more problem in moving assembly of permanent magnet moving coil instrument. Okay, so shunts, I'm giving the answer with respect to a PMMC instrument. So the best possible answer for this is option C according to this. So it's manganese. Okay, is the correct answer. Okay. Next. Okay, yes. Okay, that's an expected problem. So it's happening immediately. The material used for springs in PMMC instrument. Okay, so we have the moving coil. So we have a so this is how we get the NPMMC. So I'm talking about only the moving assembly. So what we have is a cylindrical soft iron core. That's a moving assembly. And over this we have the aluminum former. Little bit of constructional features. Okay, we have the aluminum former on which we are going to have the moving coil. Okay, put your aluminum former. In this we have a N-turn moving coil. Okay, so this is your coil having n number of turns. That is the one carrying the current in the PMMC instrument. So we have two wires to carry the current sensed by the PMMC. Okay. Yes, actually I should have not connected this now. So then we have a spindle to hold the entire moving assembly. Okay. So then we are going to offer control springs to offer a controlling torque. So it is attached to the spindle. and another end is rigid. Okay, similarly here, okay, we have the spring. Okay, that's rigidly fixed. So by the time the spindle rotates, it is going to offer a controlling torque at steady state. The controlling torque will balance TC of T will balance TD of T. That's where the steady state pointer deflection is going to happen for the input current. So how we are going to pass this current means we're going to connect the current only to the springs. Okay, so that is going to service springs are going to service current carrying mechanism as well. Okay, so that because it is not going to disturb your moving assembly, this is how we pass the current. Okay, therefore the springs should be made up of material. Okay, they are going to offer very low resistance because effectively what resistance we see is the moving coil resistance. That's going to be the meter resistance. Okay, there may be some shunts we are connecting along with that. It is going to make a resistance. As of now, the moving coil resistance is going to become your meter resistance. Okay, so now the current which we are about to pass to the moving coil is passing through this. Then we are going to connect a wire here, and then we are going to connect a wire here. Okay, right? Okay, like this. Okay, so that now the moving assembly won't get disturbed. Okay, so we pass the current to the moving coil only through the two springs. Okay, so this is going to have a stiffness K by 2. This is also going to have the stiffness K by 2. The net spring stiffness we are going to take K. Okay, so they have the responsibility of offering such a stiffness. At the same time, they have the responsibility of passing the current to the moving coil. They play a dual role. Okay, right? The two springs are serving two important purpose. One, they have to pass the current to the moving coil. At the same time, they have to offer required stiffness. Okay, right? So when they are passing the current through the moving coil, and they should be made up of material, they are offering very low resistance. The resistance offered by the springs, okay, for the entire instrument should be very small. So we are looking for an alloy. Okay, that's what the alloy we call it as Pasper bronze. Okay, that's a material we use for making springs. Okay, so springs are made up of Pasper bronze alloy. They are very good conductors as well as they will offer the stiffness. And remember, the current is passing through this. So definitely there is going to be a I square R loss across your springs. So once the springs are getting heated and we have a real problem mechanically, the stiffness will decrease. So then the pointer will deflect little more than what it has to deflect. So to avoid all those problems, we use such a material. So that is what we call as Pasper bronze. Okay, so that's a material for springs in PMMC instrument. Okay, so related to the constructional features of a permanent magnet moving coil. Okay, not to forget that we have a north and south, okay, permanent magnet poles in this assembly. Okay, right? So under the influence of strong permanent magnet flux only, we place this soft iron core. Okay, right. That's a simple thing. Yes, so that's a correct answer. Then the next one about again one more instrument, a transformer for instrument. Okay, so we call it as generally instrument transformer. So what we have is a current transformer. So this may be the current, like this is the current to be measured, and here we will have a winding. That's a core of a CT. Okay, so this is where we are going to have the winding. Okay, so this is where we are going to have the ammeter. Okay, so assuming it's a AC current, we're going to have a AC ammeter. Okay, so this is the current to be measured, maybe a 0 to, for example, 20 amps. So you can step it down. For example, this is to 0 to 1 amps. Okay, so 20 times you can step down by using CT. Okay, to the safe level. Okay, so then we are going to connect the instrument. That instrument itself, we call it as a burden. That instrument itself, we call it as a burden. That's a burden we connect it to the secondary of a current transformer. It's basically an instrument. So that instrument is going to have a range of 0 to 1 means then the burden will be known as 1 amps burden. That's a maximum. Okay, so it is going to have the internal resistance. The resistance of the ammeter only going to act as a burden. Okay, so burden of a current transformer is expressed in terms of what means simply the secondary current, winding current only. That's a correct answer. Okay, so secondary winding current is nothing but your maximum secondary winding current should match your full scale deflection current of the instrument, which we connect always into the secondary of instrument transformer. That's a current transformer in this case. That's a simple problem. Once you know the CTPT, okay, so then you can. Yes, the final stage of one from analog electronics, the final stage of a multi-stage amplifier uses. Okay, so the final stage as the, when you have a multi-stage amplifier, the final stage has the responsibility. For example, assume it is like an audio amplifier. Assume it is like a audio amplifier. A simple example I can pass. Assume I'm addressing a mass of students through a mic that is going to pick the audio signal of range 20 hertz to 20 kilohertz. That's your audio signal frequency. Just know that, okay, since they're asking in the problem electrical EEG frequency also, they may ask audio frequency range also. Just know this on the way. 20 hertz to 20 kilohertz is the audio frequency. Then we have a weak signal produced by the microphone. Then it will be amplified by a small signal amplifier usually. Okay, there will be a small signal amplifier. So since it is talking about multi-stage, so there are multiple stages of amplifier. I'm giving one simple application of a multi-stage. This is a small signal amplifier will have some gain A1. Like that, there are multiple stages, and finally, when it comes to the final one, that is the one responsible to drive the speaker, for example. Okay, that's where, okay, so I can play the music or whatever I'm speaking will be audible to the mass of students. Okay, a group of students. Okay, so this is the final amplifier is talking about. This is a multi-stage amplifier, the final stage. So like that, n number of stages are there, and this is what we call as the final stage. What's the responsibility of the final stage means? The final stage must be capable of delivering raw power to the load. This is your load. The final stage must be capable of delivering raw power to the load. So raw power to the load means the final stage amplifier should offer such a huge efficiency. Okay, that means this amplifier will be excited by VCC. Okay, so that means there is going to be efficiency calculation. So whatever the AC power delivered to the load divided by the DC power drawn from the DC powered supply, average DC power drawn from the power supply into 100%. That's what we call as a percentage efficiency. Okay, but in this case, what we're going to have is going to be like a AC signal, something like that. So this amplifier, so this is what very technically we call this by the name power amplifier. The final stage of any multi-stage is going to be a power amplifier. With respect to the electrical, I'm feeling, okay, assuming it is the final stages, driving a speaker in a simple music system, okay, in a public address system. So it is a power amplifier. With respect to this, I can go for the answer. So power amplifier means the efficiency of the power amplifier should be as much as, that means as high as possible. Okay, there are multiple amplifiers like class A, class B, class C we have. So let me refer only the class A. So if you have a class A power amplifier, its efficiency is very worst, normally maximum is 25%. But by using transformer coupling, it is possible to double the efficiency to 50%. With respect to that, I'll go for the coupling as transformer coupling. Okay, so, and there is a benefit of using transformer coupling. The application may not be the same as the designer. He might have thought this or something else also, but I'm giving the fundamental connecting to the problem. So the multi-stage, and he's talking about the final stage. I have took one example of a multi-stage. Then I'm seeing what is the final stage. That's a power amplifier. The power amplifier should be capable of delivering a huge efficiency, and considering a class A. Okay, so it's worst in case of, because it has a responsibility to pass the input signal as it is to the output. So if we call this as signal Vx, and this also going to be Vx. Yes, it has to pass it as it is, but at the same time it has to meet the power demand of the speaker. So whereas the previous stage amplifiers cannot meet this power demand. So the transformer coupling maximizes the efficiency. That's one objective of using transformer coupling. There is another benefit, depends on the applications. Okay, so purpose of choosing a transformer coupling in the final stage is to improve the efficiency, and one more benefit is to offer a complete isolation. Okay, for example, you can think of okay, someone picking ECG signal, okay, so using electrodes means, and there is a signal, okay, we are connected electrically as a human, we are connected electrically through the electrodes to the system, okay, amplifier system, and we are going to have an ECG amplifier that is going to pick the ECG signal from us. Okay, so if there is a good isolation between the next stage and the present state, then we are isolated. In fact, we are insulated. We are insulated means we are protected. Okay, so transformer coupling offers such a protection because of its isolation is nothing but completely insulated from the rest of the circuitry. So transformer coupling perfect for that purpose as well. So two important reasons why one should go for a transformer coupling in the multi-stage. Okay, right? So that means the world it is going to interact is going to be little different. As of now, I said a speaker application there, okay, the transformer coupling is going to improve the efficiency, but some other application, so it may be the human interface. Okay, that means there may be some connection to the human being, so try to maintain a complete isolation between the two world. Okay, so transformer coupling will offer such a insulation or isolation. Okay, right? So sometimes this is called isolation transformer in that application. Yes, that's a point why I am choosing the final stage as a transformer coupling. Okay, that's a very good problem. Connecting to the fundamental. Yes, then this one, a node voltage analysis can be carried out on. Okay, so node voltage analysis can be carried out on planar and non-planar networks. Okay, so that means, for example, planar means, what is a planar network? For that, you need to have an idea. Planar network means, so whatever you see on the screen, it's a plane. Okay, we can call it as a plane. It's a surface. So can I draw a circuit in the surface? If I give a circuit represented in this plane, okay, that's a 2D. Okay, so we have y-axis, we have x-axis. In this 2D, if I plot, okay, if I draw a circuit, that's a planar circuit. Okay, for example, if I draw a circuit like this, then this is known as I can draw like this. Some circuit I can draw. Yes, this is a planar circuit excited. Yes, that's a planar circuit excited by a DC I can. Okay. Suppose if I connect a wire here with a resistance like this also, I'll connect. So then, so definitely you need a different view. It seems to be a non-planar because of this wiring. So we can still make it planar. Planar means we can connect this way. Okay, instead of that resistance, you can connect this way. Still, I can put the circuit in this available surface. Okay, without any crossing. Okay, so yes, this is still okay. It was looking like a non-planar, but I can still make it as a planar circuit. This is a good example of a planar circuit where one can go comfortably with the nodal analysis. Okay, node voltage analysis, nothing but nodal analysis. I'll give you one more example. Say, for example, something like this. A non-planar circuit means something like this. So, cuboid, let me represent something like this. Okay. Yes. Like this. Okay. Hope you understand. So refer only the dark connection. I can give you, okay, yes, so many resistors, 3 and 4, 4. Okay, total 12, 3 into 4, 12, yes. So this is a good example of a non-planar circuit. Okay, I can connect like this also. Yes, that demands a 3D view. That demands a 3D view. Okay, there are many crossings. You have to carefully view the circuit, but still you can go with the nodal analysis. This is a planar circuit. This is a non-planar circuit. Okay, you need, yeah, one more axis. Okay, a 3D view you need for the circuit, a 3D view or 4D view, but anyway I'm restricting myself only to this is the 2D view and this is the 3D view, the one which is not in 2D view. Okay, we can call it as a non-planar circuit. Yes, both the circuits I can analyze comfortably by using nodal. So the answer is node voltage analysis can be carried out on both planar as well as non-planar circuit. Okay, right? Refer only the dot connection in this. Okay, these are the connections points. That's all. So nowhere else you have any other connection. That's it. Okay, yes, that's a very good example. Yes, then, okay, so frequency range of EEG signal. Okay, so and no electrical students will have an idea unless otherwise you might have studied an elective called biomedical instrumentation. Okay, that too, even if you studied, remembering the range is not very easy, and probably less number of students attempted correctly this problem. Still, you have to go with the guess. Okay, so but anyway, the right answer for this problem is as per the reference available. Okay, in okay, open source, I can go with the answer 0 to 100 hertz is the correct answer. Okay, so I'm not talking about the EEG signal. Okay, there are multiple like alpha, beta, gamma, like that. There are ranges of EEG signal. You can just Google and you will be aware of those things. So just passing the key for this, the frequency range of, okay, and the brain signal. Okay, so we call it as, you just check it, what does EEG stands for. Okay, right? ECG, electrocardiogram, like that. What is your EEG? EMG is the electromyogram, muscle activity. This is the brain activity. EEG is the brain activity. So electroencephalogram, like that, it will go. Just Google and have an idea of. See, in fact, what is EEG itself? Okay, we are not aware of. Then talking about the frequency. Okay, so less number of students only attempted this kind of problems. Okay, right? So with this, let me conclude this video. We'll update you with one more video for the rest of the problems. Okay, so hope you are enjoying the content delivered, and do subscribe our channel and look for the updates from us. Okay, thank you.